3 small earthquakes have shaken southeast Missouri since August 14th, bringing fresh attention to a seismic zone capable of cutting river crossings, roads, pipelines, power, and water across the central Mississippi Valley. The largest was magnitude 2 near Catron on August 15th. Yet one of the huge 1812 ruptures crossed the Mississippi River 3 separate times inside what USGS research calls the most seismically active part of North America east of the Rocky Mountains. A modern repeat could isolate communities, block freight, and damage lifelines across several states. For generations, the story centered on the Mississippi appearing to run backward. Modern planning centers on bridges and soft river ground. The weak point may be steel, soil, levees, or buried utilities. And the reason New Madrid shaking travels so far comes later. But first, the fresh activity needs context. The magnitude 2.2 Catron earthquake on August 15th was reviewed by the USGS at a depth of about 5 miles. The magnitude 1.8 event near Marston on August 14th was also about 5 miles deep, and another magnitude 9 event occurred nearby earlier that day. The University of Memphis Center for Earthquake Research and Information continuously monitors the New Madrid region as part of the Advanced National Seismic System. Small earthquakes are normal there. They do not provide a clock for the next major event, and the USGS says major earthquakes cannot be predicted by date, location, and magnitude. That distinction is critical because New Madrid is dangerous without any prediction. The seismic zone runs through the central Mississippi Valley between the Memphis region and the confluence area farther north. USGS paleoseismic work has found evidence that the zone produced magnitude 7 to 8 earthquakes about every 500 years during roughly the past 1,200 years. That is not a countdown. It is evidence that the 1811-1812 sequence was not the only large sequence preserved in the geologic record. The historical sequence came in waves. Large earthquakes struck on December 16, 1811, January 23, 1812, and February 7, 1812, with major aftershocks mixed into the sequence. Modern USGS estimates place the 3 principal shocks in roughly the magnitude 7 to upper 7 range, with uncertainty because no modern seismometers existed. The February event was especially important to the river story. USGS says uplift on the responsible fault created a scarp that crossed the Mississippi 3 times, temporarily damming water in places and producing waterfall-like effects in others. That is the first payoff. The river did not literally reverse because an earthquake pulled it backward for miles. Sudden deformation, bank collapse, waves, uplift, and temporary blockage changed local flow. The same event produced widespread ground failure. Contemporary accounts describe banks caving, fissures opening, land sinking, water and sand erupting from the ground, and large waves overwhelming boats. The geography was sparsely populated then. The same corridor now carries far more people, freight, utilities, roads, bridges, ports, and pipelines. The next question is what modern system is most exposed at the start? In a 2007 congressional statement, USGS scientist David Applegate warned that at least 1 highway bridge and 1 railroad bridge across the Mississippi were unlikely to survive a major New Madrid earthquake in the scenario then being evaluated. The statement also identified highways, bridges, oil and gas pipelines, and other lifelines as major concerns. That does not mean those exact bridges are guaranteed to collapse in a future earthquake. It means river crossings have long ranked near the top of federal vulnerability planning. The fault geometry makes the bridge question more complicated than a single line on a map. The planning model divided the New Madrid system into 3 major pieces: a northeast segment, the real foot thrust segment, and a southwest segment. The magnitude 7 catastrophe scenario assumed rupture across all 3. That is a severe planning case, not a statement that every future earthquake will rupture the entire system. Different segments would put different communities and crossings under the strongest motion. A bridge that performs well in one rupture pattern could face a very different demand in another, especially where soft sediment amplifies shaking or riverbank ground spreads laterally. That is why first means first loss of function in a cascading network, not one structure pre-selected to fall. A later FEMA-funded study led by Amr El-Nashai at the Mid-America Earthquake Center modeled a magnitude 7 New Madrid scenario across the central United States. It estimated that roughly 15 major river bridges could be damaged and impassable. Across the broader highway network, the scenario produced more than 3,500 bridges with at least moderate damage, and about 1,250 with complete damage. In the model, damaged crossings along the Mississippi could effectively split the response region, making it harder to move rescue teams and supplies, fuel, and evacuees from one side of the river to the other, but steel and concrete are only part of the problem. The second payoff sits in the soil. USGS geologist Eugene Schwag has emphasized liquefaction as a major New Madrid hazard. Water-saturated sand and sediment can lose strength during intense shaking. The surface can settle, spread sideways, crack, or eject sand and water. Lateral spreading is especially dangerous near riverbanks because ground can move toward an open channel. USGS identifies that process as a common cause of earthquake damage to bridges, roads, and buildings. That means a bridge can lose service even without a dramatic mid-span collapse. Approach fills can settle, abutments can shift, foundations can be pulled by spreading ground. Pavement can break at the transition between stable and moving soil. A structurally standing bridge with failed approaches can still become unusable. The same ground deformation can distort rail lines, damage port walls, and rupture buried pipes. The historical footprint shows why soil failure cannot be treated as a side effect. USGS mapping estimates that sand blows formed across roughly 4,000 square miles during the 1811-1812 sequence. That is direct evidence that liquefaction was regional, not confined to one riverbank. Modern bridges, buried utilities, railbeds, and road approaches now occupy that same broad sedimentary environment. The 2009 regional scenario shows how quickly those failures can connect. It estimated nearly 425,000 breaks and leaks across local and interstate pipeline systems. About 6 million households were modeled without electric power immediately after the event, and about 1 million without water. The study also estimated damage to more than 9,700 communications facilities. These figures are scenario outputs, not a forecast of what will happen in the next earthquake. Their value is in showing how many systems can fail together when the same shaking footprint hits the same river valley. Transportation becomes the next bottleneck. The model estimated 232 damaged port facilities and 143 damaged airport facilities. Rail facilities and rail bridges were also affected. Memphis matters because its freight network combines river traffic, major highways, rail corridors, and a globally important air cargo hub in one metropolitan area. If bridges are restricted, ports damaged, rail lines distorted, and airport surfaces affected by ground failure, the disaster is no longer local. Supply chains begin rerouting around a broken transportation node. There's another layer, levees and dams. The same scenario estimated 96 damaged levees and 327 damaged dams across the 8-state study region. Those numbers do not mean the Mississippi levee system would simply fail everywhere. They show why shaking near water creates secondary risks. A levee section can be damaged by settlement, cracking, or foundation failure. A road may survive the first shaking and then lose access because a nearby embankment or water control structure is compromised. This is why the phrase, "what breaks first," has no single guaranteed answer. The first visible failure might be a bridge component. The first network failure might be a blocked highway approach. The first utility failure might be a buried water line. The first major transportation loss might come from liquefaction under a port, railbed, or runway. Location, rupture direction, soil conditions, structure age, retrofit history, and shaking intensity all control the sequence. Now the third payoff. New Madrid shaking can reach much farther than a similar-sized earthquake in much of the western United States. USGS work comparing the 1811-1812 earthquakes with the 1906 San Francisco earthquake found an enormous difference in felt area. The New Madrid shocks produced intensity 5 or greater effects across an estimated area near 965,000 square miles, while the comparable San Francisco figure was about 58,000 square miles. Central and eastern North American crust transmits seismic energy more efficiently, so damaging or strongly felt shaking can spread across a much larger region. Modern simulations reinforce that concern. A USGS-led 2015 study tested 20 plausible New Madrid earthquake scenarios ranging from magnitude 7, 0 to 7. The simulations showed strong, prolonged shaking in cities including Memphis and Little Rock, depending on the rupture. This is not a claim that one of those scenarios is about to happen. It is an engineering answer to a preparedness question. How hard and how long could the ground move if a large fault segment ruptures? The 2023 National Seismic Hazard Model, released by the USGS in 2024, keeps the central United States inside the national earthquake risk picture. Lead author Mark Peterson described the model as a major update built from improved fault information, geology, and computation. The model is not a prediction tool. It estimates the chance and intensity of future shaking for engineering and public policy. The older New Madrid probability estimates are often misunderstood in exactly the same way. USGS testimony has cited about a 7 to 10% chance of a repeat-sized major New Madrid earthquake over 50 years, and about a 25 to 40% chance of a magnitude 6 or greater event over the same period. Those are long-term probabilities, not a deadline, and not evidence that the August 2026 small earthquakes are foreshocks. Morgan Page and Susan Hough of the USGS also found that continuing small earthquakes in the zone are not well explained as a simple tale of aftershocks from 1811-1812, supporting the view that the region remains seismically active. The human scale is why planners keep returning to the same scenario. The FEMA-funded 7 study estimated nearly 715,000 damaged buildings across 8 states, about 86,000 total casualties, including roughly 3,500 fatalities, and about 2 million people displaced 3 days after the event. It estimated about 2 million people seeking temporary shelter and direct economic losses near $300 billion. Those figures came from a specific modeled rupture inventory, time of day, and assumptions. A real earthquake would differ. The purpose is not certainty. It is stress testing the systems most likely to be overwhelmed. Emergency response is exposed to the same cascade. In the 8-state scenario, 129 hospitals were estimated to suffer at least moderate damage and 32 complete damage. The model also produced at least moderate damage at 729 fire stations and 379 police stations, with 177 fire stations and 136 police stations completely damaged. Search and rescue demand was estimated at about 42,000 personnel organized into 1 to 1,500 teams. Those numbers matter because bridge and road failures do more than interrupt ordinary travel. They can separate damaged neighborhoods from the hospitals, fire stations, fuel, water, shelters, and outside crews needed during the first days. And that brings the triple river crossing back into focus. The old fault trace is not dangerous because the number 3 has some mystical meaning. It is dangerous because the Mississippi Valley concentrates soft sediment, water, transportation choke points, and buried lifelines in the same corridor where large earthquakes have happened before. The 1812 rupture physically changed the river landscape. A modern rupture would meet a landscape covered with infrastructure that did not exist then. Right now, the verified situation is much less dramatic. Small earthquakes continue to be recorded in southeast Missouri, including the magnitude 2. 2, Catron event on August 15th, and there is no scientific basis for saying a major New Madrid earthquake is imminent. The unresolved issue is not whether the August tremors are a countdown. They are not. The unresolved issue is how a future large rupture would cascade through modern river crossings, soft ground, utilities, and freight networks, and which weak link would lose function first. That is what agencies and engineers continue to model. Not an exact day, but the consequences of a low-frequency, high-impact earthquake in the central Mississippi Valley. Subscribe for the real numbers on the next one.